on Cmen846 Advanced Testing Methods and Reliability of Electronic Systems. This is our lecture number 7, as I have said, and it will be continuation of our lecture number 6. Good day, ladies and gentlemen.
To start with assessment of reliability of electrical or electronic equipment. As we all know, an equipment is made up of different components. So if we want to assess the level of its reliability, these are the steps that we should follow. The first thing is to give a list of all the components in the equipment and also state the basic failure rate of each of the components, and then multiply each component by the number of it's the same type we have, like resistor, multiplied by whatever they are, 20, 30, and then multiply all the available weighting factors given. As we have seen, we have environmental, we have temperature, and we have rating weighting factors. And then after that, you now come and add all the products obtained from stage 2, stage 3, and stage 4, and finally use the formula for calculating the reliability. For us to understand this better, let us look at an important thing here. That is, after determination of the reliability, if we are asked to find the mean time between failure, we know it is the reciprocal of the overall failure rate. Now, this is the worked example number 7, which says an electronic device works for the whole day, that is 24 hours, and continuously for 50 days. The electronic components in the device and their basic failure rates are given here. We have transistors, their number, their basic failure rate, and the weighting factor. This is the rating weighting factor. That of diodes, that of capacitor, resistors, and connections, which are the soldered joints. They are also considered as components. Now, we are also told that the temperature weighting factor environmental weighting factor for each component is 2.0, and the temperature weighting factor is 1.5. And then we are asked to calculate the reliability for the operation of 50 days period. Now, these are what were given in the previous table: the components, the number of each component, and then the basic failure rate of each of the components. So the next thing we'll do is to create a column for environmental weighting factor, which is common for all of them, another column for the temperature weighting factor, which is 1.5 throughout, and the rating weighting factor is already given for each individual component. It is only the connections, the soldered joints, that don't have anything like rating weighting factor. Now, the overall reliability or the failure rate is now found by saying, let us take a transistors for example. They are 30 multiplied by their basic failure rate, which is 0.08, multiplied by the environmental weighting factor, multiplied by the temperature weighting factor, and then multiplied by the rating weighting factor. And doing that, we got 14.4 for the transistors, for the diodes, for the capacitors, for resistors, and for the connections, that's the soldered joints. All their overall failure rates are obtained here. So the next thing is now to find the summation of all the failure rates of these individual components, and adding this and this and this, we got 68.4%, and we know it is per 1,000 hours. Now, if I want to evaluate my reliability, first of all, I'll get the total operating time, which is 50 complete days. That's 24 times 50, which gives 1,200 hours. Now, the reliability, this is the formula, R equal to exponential minus lambda t. This t is a subscript standing for this total, and this t is for the time. Now I'll bring my reliability, look at it. You know, it is 68.4 per 1,000. Since it is per 1,000, I'll say times 10 raised to power minus 3 to take care of that per 1,000, and multiply the hours. We got 1,200 hours. Now everything gave 0.44. If I want to express it as percentage, it should be 44%. So the next thing is we are going to look at the methods of prediction of reliability of interconnected systems. By interconnected systems, we mean a system that has different stages, and these stages are connected in two different ways. The first way is what we call the series connection, and the second one is what we call the parallel connection. Of course, there is third one, that is combination of series and the parallel. So now, how are we going to get the reliability for a system where the components are connected in series, where the components are connected in parallel, and where the components are combination of series and parallel? Now, a series connection, which is number one, we know if they are arranged in series, they should be like this diagram A. We have A, we have B, we have C, they are in series. So my signal that I want to transmit from this point to this point, it has to pass through A, B, and C. Meaning, whenever either A or B or C fails, the overall system has failed. And the second one is the parallel system. If you look at it, just look at it as you have resistors in parallel. And I want to transmit current from this point to this. It means the current can go through A, can go through B, can go through C. And it means we need at least one of them to be intact for the system to continue to operate. That is the parallel system. We need at least one of them to be operating for the system to continue working well. And the last one is this combination of series and parallel. Look at this. My B and C here, they are in parallel to one another, but their equivalent is now in series with this. So these are the three methods. So how do we get their reliabilities? We use the laws of probability for ascertaining the reliability of the systems. Let me start with the product rule. This product rule is a formula that we use for systems which are in series. As you can see here, we are saying A and B and C, all of them must be what? Intact. And means product. Therefore, the reliability for this series system should be probability of A times probability of B times probability of C. If any one of them is 0, then the overall probability should be equal to 0. And we also call this rule as multiplication rule of probability. Let us demonstrate how we use this formula, which worked example number 8. The question says the probabilities of successful operation of unit A, B, and C are 0.94, 0.92, and 0.97 respectively. What is the probability for a series system containing A, B, and C to operate successfully? We have said this should be the product rule, meaning the probability for ABC system to work should be probability of A times probability of B times that of C. I put the values given to me and I got 0.84. So one thing that is very important for us to note here is that look at the resultant probability. It is less than this, it's less than this, and it's less than this. Therefore, whenever you are finding the reliability for a series system, you see that the overall reliability is less than that of any individual, and this is because all of them are needed to be perfectly operating for the system to be operating well. Now the second rule is what we call the addition rule of probability, and this is a rule that is used for systems which are connected in parallel. As we know, in parallel it is either this one to work, or the second one, or the third one, or the nth one. Not all of them. Only one of them working will make the system work perfectly. So supposing I have two systems A and B, the probability for the system to work should be probability of A addition, that's plus probability of B, but I have to take their common intersection to be mutually exclusive rule. That is where we have A and B, the intersection have to be deducted. This formula, if we wish, we can express it as this, because expand this bracket, it will give you this. So based on this, for two systems, it means if I have n units connected in parallel, my overall probability should be 1 minus 1 over 1 minus PA times 1 minus PB up to what? PN, depending on how many we have in parallel. Now, knowing these two rules, that is the addition and the multiplication rules, we are going to evaluate the reliability and the failure rate on mean time between failure for series system first, and then we'll go and do that for the parallel. In the series system, we know if we have n units and each one has a probability R1, R2 up to Rn, you know the overall reliability of the series should be R1 times R2 times R3 up to what, Rn. And we know this reliability R is equal to exponential minus lambda t. This is lambda 1, this is upon lambda 2 up to lambda n. So for me to find the reliability, all I need to do is wherever I see R1, I put this, R2, I put this, Rn, I put this. It should be multiplication of all of them. So I'm multiplying exponential functions. The rule says I should take the exponent and add all the powers. If you do that, you end up getting this. So here I am having summation of lambda 1, lambda 2 up to lambda n. So I can say my overall failure rate for a system that is in series, it is a summation of the individual failure rates, that is lambda 1 plus lambda 2 plus lambda 3. And I can remember that my mean time between failure is reciprocal of the overall failure rates. Therefore, it should be 1 over lambda 1 plus lambda 2 up to lambda n. And there is one thing we need to note. We put R1, R2, R3 here, assuming they have different failure rates, they have different probabilities. But if the system are all identical, you see that lambda 1 is equal to lambda 2 is equal to lambda n and is equal to lambda n. So therefore, all I need to do here is whatever they are, I will say n times lambda, multiplying them by the number, because all their failure rates are the same. And from here, my mean time between failure should be the reciprocal of that, which should be 1 over n lambda t. Of course, the t is not supposed to be here because the mean time between failure is only 1 over what? Failure rate. Therefore, t is a mistake. We should remove it. Now we go to the level of determination of reliability, the failure rate, mean time between failure for systems which are connected in parallel. If you remember, we said the probability for those systems in parallel is 1 minus into 1 minus R1 into 1 minus R2 up to 1 minus Rn. So if we have only two of them, it should be only R1 and R2. And you know, if I expand this, they are going to give me R1 plus R2 minus R1 R2. Now let me assume my R1 is equal to exponential minus lambda 1t. The other one should be exponential minus lambda 2t. Now substituting them here, my overall probability, which is the reliability, is exponential minus lambda 1t plus minus exponential lambda 2t, and then plus the product of the two. Now these products, we apply the law of exponential. We take only one of them and add their powers, so that I will have minus into lambda 1 plus lambda 2 times t. And if I want to find my mean time between failure, is not as easy as that of the series system. So therefore, the mean time between failure should be integral of the reliability from time 0 to time infinity. Now, bringing this my reliability under this integral notation, I finally got this 1 over lambda 1 plus 1 over lambda 2 minus 1 over the summation of two lambdas, that is lambda 1 and lambda 2. So from here, if you have a parallel system with n units, the one we have done here is just for 2. So if it has n units, my overall mean time between failure should be this 1 over lambda plus 1 over 2 lambda plus 1 over 3 lambda up to the last. Had it been there only 3, we terminate at this point. If it is 2, we terminate at this point. But if it is n, you continue like that. So as we have seen, we have 3 possible interconnections: series, parallel, and combination of series and parallel. Now for the combination of series and parallel, my overall reliability should be the product, which is R1 R2 times Rn, and for the parallel is 1 minus into bracket 1 minus R1 into bracket 1 minus R2 up to what? 1 minus Rn. Now if I want to find the overall reliability, all I will do is find the parallel, find the series, and now come and multiply them, because the parallel is now in series with the already series system. So I have something like this. For me to find my mean time between failure, I have to integrate my reliability, and you can see here I'm maintaining my n. That is why I cannot give any expression in terms of lambda, depending on what is your n. Now, having seen this, we go to worked example number 9 that will highlight some of the things we have seen. And the question is saying we should compare the reliability of a series system with a parallel system. And how many units do we have? We have 3 units, and their respective reliabilities are given here: 0.93, 0.87, and 0.78 for the 3 systems. So you know, for the solution, if they're in series, it should be R1 R2 times R3, which gives me 0.639. As I have said, the resultant is always less than the smallest one. And for the parallel, I'm going to use 1 minus into bracket 1 minus RA into 1 minus RB into 1 minus R3. In fact, I'm supposed to use R1 R2 as I have used this here, so therefore there's a mistake. But substituting these values, you can see my resultant reliability is 0.998, and this 0.998 is bigger than this biggest one, which is 0.93. What are we being told here? The fact is that the reliability for parallel system is much higher than that of what? Series connected system. Another example, question number 10 says we have an advanced communication satellite and it has inbuilt microwave repeater, and the mean time between failure of that repeater is 40,000. The link is operative if one channel is working, and the reliability of the switching unit is taken as 0.95. Now, we are asked to determine the reliability for operating for a period of 1 year when we have A, single channel, B, 2 parallel channels, and C, 3 parallel channels. So the first thing I will do, I'll take my given mean time between failure 40,000, take its reciprocal to give me my failure rate. I go 2.5 times 10 to the minus 5. And we are asked to evaluate the operating period of what? 1 year. That is 24 hours times 365 days. That give me 8,760 hours. Now, my basic reliability should be R equal to exponential minus lambda t. This is my lambda, this is my t. Substituting, I got 0.803. That's the basic reliability for the unit. But we are told to use single, 2, and 3 parallel units. Now, let us start using this one is for the single, and the one we are going to look at now is for what? The parallel. So for the parallel, I have 2 of them. I should have 1 minus into bracket 1 minus R1 into 1 minus R2. But I didn't put R1 and R2 because it is the same unit that we used twice, 2 of them, 3 of them. So the reliabilities are the same. Now, the basic I have got is 0.803. So I'll see 1 minus into this and this. Finally, I got 0.961. You should notice that for a single system, I have only 0.803. But when I take 2, it improved from 0.803, which is 80%, to about 96.1%. And we know this one, the 2 units, they are now being operated by a switch. So the switch is like in series with them, and the reliability of the switch is given as 0.95. So I should say my overall reliability, taking the switch into consideration, should be the product of this and 0.95, which give me 0.913. Why do we get the reduction? Is because the relay is not perfect, the reliability is not equal to 1. Now we are asked to do the same thing using 3 parallel units. So it should be 1 minus R, 1 minus R, 3 of them. After evaluating, I got 0.992. We can see when it is 2, we have 0.961. When it is 3, we have 0.992. What are we seeing here? The reliability is increasing with the increase of the number of units connected in parallel. Also, this one is in series with my switch, so I have to multiply it by 0.95. I got 0.942, which is equivalent to 94.6 reliable. Another example, worked example number 11 says an electrical power system has 3 sections which are connected in series. The mean time between failure of the sections, that's the 3 different sections, is 10,000, 5,000, and 4,000 hours respectively. we are asked to evaluate the overall mean time between failure. So what I will do is to say, okay, their overall failure rate, it should be summation. Why? Because we are told that the systems are connected in series. So the lambda 1 should be 1 over mtbf1. That's 1 over 10,000, which gives this. Lambda 2 1 over 5,000, lambda 3 1 over 4,000 give this. So I can now see my total failure rate is the summation of the 3. And if you find that total failure rate, you take it reciprocal, it will give you overall mean time to between failure. And I got 1,818. Can you see that one system has up to 10,000, second one have to up to 5,000, and the last one is the smallest, it has 4,000 hours. But because they are connected in series, the mean time has reduced drastically to 1,800. What is this suggesting also? Systems connected in series, they are not much reliable. What example number 12 says we should calculate the mean time between failure of a system given in the following diagram. If you look at this diagram, I have 3 units, this one, and this. 2 of them are connected in parallel, and whatever is the resultant, it is in series with this. So I should start by saying, okay, let me find the reliability of these 2 in parallel multiplied by that of series, it will give me the overall reliability. Now, for these 2 systems which are in parallel, the equivalent reliability is equal to this. We have seen this formula severally. So if you expand this one, it will give you 2r minus r square. And if this 2r minus r square is multiplied by the reliability of this one, which is r, it should give me 2r square minus r cubed. But we know r is equal to exponential minus lambda t. So I should have 2 exponential minus 2 lambda t minus exponential minus 3 lambda t. And if I want to find the mean time between failure as I am required to, I will say it is integral of this my overall failure from 0 to infinity. And using the method of integration of what? Exponential function, you are going to end up getting this, which is equal to 2 over 3 lambda. And if you look at this one, my mean time between failure, you can see it is 2/3 of what we are supposed to have for a single unit. The reason why it is not up to 1 is that, you know, these 2 connected in series, they have increased it above 1, but since in parallel, but since these 2 are in series with this, the effect of the series bring it down drastically. So we are now going to discuss another aspect which is very important in reliability, and they call it redundancy. What is this redundancy? A redundancy is just a technique of providing more than one means of getting an equipment to perform its function. That is, if you want to do something like production in a company, instead of having only one machine to do it, you can have 2 or 3 of them. You can decide either to share the load among them or to make one of them start working. Whenever there is failure, the second one will take over. So that is what we call redundancy. And this redundancy makes a system to continue to work even if one of the items or some of the items have failed, because we have substitute. And the redundancy is used when other methods of improving reliability are exhausted. That is, it is not the first choice, it is not the best choice. If there is any way you can improve the reliability of your system without introducing redundant segments, do it. But if they are not there, then you can use the redundancy. Or even if they are available, if you compare it with the cost of using redundancy and the cost of other methods, if the cost of redundancy is cheaper, you can employ it. And this redundancy has many advantages, which include plant maintenance. That is, if you have many machines, you can stop one of them from working on the other one and you maintain the other one, do some repairing so that it will be perfect and continue to work later. And we use it for allowing repair without shutdown. That is, shutdown time is a period when your machine is not working because of being repaired. So if you have more than one, can you stop your production? No. While this one is being serviced, the other one should continue to work. And another advantage is we use this redundancy method in emergency situations. That is when suddenly one of your systems fails or an accident happens. You cannot say, I'm going to close my company because the machines are not working. No. If the accident or emergency affects only one or some of them, you can use the other ones that are working perfectly. But at the same time, this redundancy, it has some limitations, that is disadvantages. The first one, it increases the system weight, of course. If you have one system, maybe it is 1 ton in weight. If you are using two, you have 2 tons, it is increasing the weight. It is also increasing the space requirement. Yes, the space required by more than one system is more than the one required by a single system. And it also increases the complexity of the systems. Yes, if I have one device to maintain, it is simpler than I am having 10 of them, so my attention should be distributed among them. Therefore, the system should be more complex. And of course, it causes increase in the cost. We don't need to say anything about this. Whenever you buy one thing, adding the second one, you are increasing the cost. It also increases the time to design. Any system that has redundancy, it is more complex, therefore it requires longer time to be designed, and it is increasing the costs of maintaining the system. The time to maintain one system is lower than that to maintain more than one. Therefore, redundancy increases the cost of what? Maintaining systems. Now, for us to have a clearer picture of this redundancy, we have this diagram showing the classifications of the redundancy. Basically, we have two classes. One is called the active redundancy and the other one is called standby redundancy. Otherwise, it is called passive redundancy. And the active redundancy is of three types. We have what we call full or parallel active redundancy, we have partial, and we have conditional, which sometimes is called majority voting active redundancy. Now, the standby, which is the passive, is of two types. We have non-operating and we have operating, and we are going to discuss all these ones one after the other. Let us start with the active redundancy. In active redundancy, all your units are activated, they are energized at the same time. The system is expected to function even if only one of them is working, but we on all of them, we activate all of them and they are working at the same time. What's the advantage then? When one of them is faulty, the others will continue to work without any problem. And another advantage is that the total load to be carried by single is carried now by all of them by sharing. So if you want to visualize the active redundancy, just look at it as a parallel electrical circuit where we have current flowing from one point to another, but it has more than one path to reach the other path. And a typical practical example of places where active redundancies are used is where what we call diversity reception. This is a method of receiving signal from a large distance. What we do is we have antennas here, we have 3 of them. They are separated at a very large distance, and these antennas, we know they are the ones that will detect the electromagnetic energy, the radio signal, and what they detected is passed through amplifiers, amplifier 1, 2, and 3. And after amplification, the outputs are now delivered to combining units. The function of this unit is to accept all the 3 of them and look at which one is stronger than the others. It will select the stronger one and pass it to the next stage for processing. So as we can see, even if one fails, still 2 are working. Even 2 fails, at least the last one is working, and that increases the reliability of the system. Now, for the active redundancy, as we said, it is equivalent to parallel connection. And for the parallel combination, you know, the overall reliability is given by this formula, as we have seen in the previous section. And mean time between failure is equal to this. We have already seen this, no more explanation is needed here. So this active redundancy, we have partial active redundancy. The partial active redundancy is the one in which we have more than one systems connected or more than one unit connected in parallel. But we don't expect all of them to be energized at the same time, but we require at least more than one to be activated at that time. For instance, if you look at an aircraft, it normally have up to 4 engines, and for that aircraft to successfully fly and land without any problem, there is need for more than one of these 4 engines to be working. So therefore, the reliability in this case, where you have many units but you need more than one of them to be operative for the system to work perfectly, we use binomial expansion technique in order to find the reliability. This is the formula R plus Q raised to power n, where R is the probability of my reliability operation, that's perfect operation, and Q is unreliability, that is the failure operation, and n stand for the number of units I have connected in parallel. Now we know that reliability plus unreliability is already equal to 1, as we have seen previously. So to demonstrate this example, let us assume the unreliability of an engine of aircraft is 0.01. So since we said the unreliability plus reliability is equal to 1, my reliability should now be 1 minus this, which is 0.99. So what is the reliability of successful flight if the aircraft can complete the flight on at least 3 out of the 4 engines? So in this case, I'll say P plus Q raised to power 4. Why? Because I have 4 engines. And expanding this one using binomial technique and using maybe Pascal triangle to get this coefficient, I got R raised to power 4 plus 4 R cube Q plus 6 R square Q square plus 4R Q raised to power 3 and Q raised to power 4. But we are told that it needs at least 3 out of the 4 engines for the successful operation. So if you look at the force here, it means all the 4 engines are working raised to power 4. And if you look at this my R raised to power 3, it means 3 of the engines are working. But anything downward here, we don't have up to 3. So this second and the first term, they are the ones I'll take to evaluate. Now my reliability should be R cube plus 4 R raised to power 4 plus R cube 4 R cube Q. My Q is given 0.01 and my R should be what, 0.99 as I've said. So let me substitute here and I got 0.999 as the probability of the flight to be successful. Then the other class of the active redundancy is called conditional active redundancy, or sometimes they call it majority voting. And this is an active redundancy where we have n unit connected in parallel, but it is required, it is necessary that out of this n we need m, where m should be greater than what? 1. For the system to use more than 1, so we say that kind of active redundancy is called majority voting. It needs more than 1. If it is only 1, no perfect operation. So this means that the more than 1 unit is required for the system to work perfectly, and in the situation where we have only 1 of them working, there is probability of what? Failure. So the next thing is we are going to look at the standby redundancy. If we say something is standby, it is just waiting. It is not doing anything now. It is waiting until maybe when the one doing something has been eliminated or stopped, then you can take over. So only one of the units is now energized. The others are what? Deactivated, and they are waiting for them, the time for them to start working. For us to understand this, let us look at this diagram. If you look at it, I have unit 1, unit 2 up to unit n. But unit 1 is already switched on, it is connected. All the others are open. So in this figure, what it means is that the system is working on only 1 unit. When there is failure in that unit 1, then this one will take over. When this fails, then another one will take over. And since there is need for this system to know when this one is not working, then to activate, there is need of sensing devices that will be sensing the situation of the operating one. Once it sees that it has failed, then it will come on. And of course, we need a switching device that will activate this one after sensing the failure of the first one. So in this case, the reliability of passive redundancy, that is standby redundancy, is calculated using the first n terms of the Poisson expression, and the formula is given by this: reliability is equal to exponential minus lambda t. If you can remember, this is the basic reliability of a single unit. Now into bracket 1 plus lambda t plus lambda square t r square plus over 2 factorial up to the last term. For instance, if I am having only 2 units connected in parallel in passive standby mode, this is my first term of the expansion and this is my second term of the expansion. They are the ones I'll take to give me my overall reliability. To understand this one, let us look at worked example number 13, where we are told that we have a computer and other similar one in standby redundancy are available for the control of manufacturing process, and they are used in such a way that one computer, if it fails, the other one will automatically switch on for continuous operation, and the failure rate of each computer is given by 0.01 per hour, whereas to evaluate the system reliability, if the operating period is 50 hours and the switch is perfect, meaning the reliability for the switching is 1. And we have 2 conditions, the first one using single computer, the second one using standby computer. Now the solution is this: for the single computer, my reliability is just the basic formula, exponential minus lambda t. My lambda is given, my t is 50 hours, I got 0.606, around 60.6%. For 2 systems, as I said, we are going to use the second term of the word poison expression, which is 1 plus lambda t. Now substituting, I got 0.909, which is 90.6. Can you see? The probability or the reliability has changed from 60.6% to 90.9% just by introducing one redundant unit, and this is showing how effective it is in improving the level of reliability. The standby reliability, as we have just calculated, it has advantage because it improves the amount of reliability of the overall system, but it has some disadvantages. The first thing is that we said we need sensing device, and that sensing device, whenever it detected the failure of the operating one, it will alert the switch and the switch will now activate the second one. That switch may be affected by the stray surges, that is sudden increase or decrease in the operating parameter that will tell the sensing device that the first one has failed, and in reality it didn't fail. So if it switch on the second system, operating of the 2 at the same time may cause damage to them or to one of them. This is one of the disadvantages or limitations. And another limitation is the fact that if you leave a system for a long time without using it, because we said the other ones are redundant until when the first one fails before they are used. So if they are left for a long time without using, they can deteriorate, meaning their quality, their strength will be reducing. And another disadvantage or limitation is the need of using a detector and the unit of using what? Switching units. The switching and the detecting unit, they are not free of charge, therefore the overall cost increases. And finally, the fault detectors and the switchings, we just assume they are perfect. They can accurately detect the failure of the other one, and the switching can accurately switch the other one, but there may be tendency that they may fail also. And these are 4 items that serve as limitation to the application of the standby redundancy. Now the standby redundancy also, it has or rather the redundancy in general, it has what we call with periodic repair. And with this periodic repair, it simply means that whenever one of the system is working, if it fails, we put on the second system in operation. As the second one is working, we are going to repair the one that failed, and even those that didn't fail, we should be maintaining them from time to time. And by doing that, you can see that you are increasing the reliability by making the devices or systems very much available at all the times. So the general failures are generally reduced if there is this periodic repair, and therefore the reliability and the mean time between failure are going to increase. And for us to demonstrate this, let us look at this graph. You can see this lower line, it is the one that we have single unit without any redundancy, therefore it is lower in terms of what? The reliability. And the upper one above it, which is the middle, is the one that has redundant unit, but there is nothing like periodic repair. But if you look at the last line here, it is the upper one, and it has the highest value of reliability at any point in time because it is having a redundant system and there is periodic repair. So the next item is we are going to look at the classification of failure, of the causes of failure to electrical and electronic systems, and this graph summarizes everything. Here we have the causes, and they are broadly categorized into two. We have causes due to environmental stresses, we have causes due to operating stresses. The first one, environmental stresses, include atmospheric temperature, generated heat in the device, humidity, shock and vibration from mechanical energy, atmospheric pressure, we have wind, air and dust, and we have effect of radiation, and also there is effect of electrostatic discharge on the components. And the other one, which has to do with the operating stresses, it includes the voltage surge, current surge, and frequency change. Now let us look at these items one after the other. Starting from the environmental stresses, we know that any component that operates in an environment, definitely they are going to be affected by environmental factors. There is no way you can live in a place and say nothing of that place have any influence on you. So they can have effects of weather, which include temperature, pressure, humidity, wind, and they can also be affected by the salinity of the seawater and similar environmental factors. And whenever this equipment is affected by this component, definitely the level of its reliability is going to reduce. And of course, any component that is, or any system that is used in outdoor environments, if it is not affected by one, it will be affected by another environmental factor. So let us start with looking at the effect of a temperature variation. The temperature in any region, we know that it varies with time. For example, in Nigeria, maybe in the northern Nigeria, during Harmattan season, the temperature is very low, and during the hot weather, the summer, the temperature is very high. So this variation in temperature do affect the performance of electrical and electronic devices. And due to the following effect it has on the components. The first thing is, we know that materials, substances, whenever they have temperature change on them, they are suffering from what we call thermal expansion or thermal contraction, depending on whether the temperature is rising or falling. And whenever the device is extending or contracting, definitely its performance is going to be affected. And also there is a chemical reaction effect. You know, chemical reactions do change with what? Temperature. There are some that absorb temperature, and there are some that produces temperature, endothermic and exothermic reaction. And of course, the effect of temperature change can cause melting of some devices, can cause softening, or can cause freezing of some devices. And of course, all this melting, softening, freezing, they have negative effects on the quality and the performance of any electronic or electrical device that is affected. So since we have seen that temperature, the atmospheric temperature has effects on the system, what are the remedies? How do we take care of this? The first thing is to make sure that the heat is dissipated, that is, the heat is removed from the electronic system, either using heat sink, which is a metallic conductor that is attached to component that generate heat so that it will take it out, or through ventilation, that is providing openings in the casing, or using forced air cooling using fans and similar devices. Another way that remedies the problem of temperature change is the choice of the components. If we select components that have lower thermal expansivity, lower thermal reaction and similar, they are going to have a negative, very small change when the temperature increases or reduces. Therefore, the quality of the device remains averagely constant. And also, we should select materials that have a very small thermal propagation, that is thermal conductivity. Because if you have a material that has very low thermal conductivity, there is ever tendency that if temperature touches one end before it reaches the other end, it will take a very long time, thereby preventing the effect of the temperature affecting the other part of the system. And finally, we have to use proper circuit designs using computer-aided design softwares that will help us design, simulate, and see how the temperature affects it, and then adjust the design until we get the perfect result. Then, after the effects of the environmental or atmospheric temperature, we now come to the effect of generated heat. What is generated heat? It is a heat which is generated internally to the semiconductor devices due to the current that is flowing through them. So when they are operating, they are supplied with watt voltages and current is flowing through them, and we know that current has potential of generating heat. This kind of heat is called heat generated by the device. And whenever this heat goes beyond the power rating of the component, that's the maximum temperature it can withstand, definitely it can cause variation in the normal operation, and it can even cause failure. And of course, any system that generates too much heat, it will have problem of quick aging. That is, it will be weared out within a very short time. So since the flow of current is necessary for the system to work, and whenever current flows, it has negative effect on the reliability. How do we remedy that? The first thing, we use good heat sink so that we can absorb the heat from the surface of the component and dissipate it away. And also choice of good component with good thermal characteristics like expansion, contraction, and conductivity. And another way which is very important is using what we call the rating concept. The rating simply means we operate our components at lower voltage, lower current, so that too much stress from voltage and current will not tamper with its normal operation. The next thing is we look at the effect of the humidity. The humidity, as we know, stands for the amount of water vapor that is existing in the air. And how do we get the water vapor? Whenever the temperature of the space increases, it heats the water from the water surfaces like rivers and streams, and that water will be vaporizing, changing into the gases and live in the atmosphere. So whenever we have this humidity in the atmosphere, so when this humid air enters the enclosure of any electronic system, there is every tendency that the heat in it will be absorbed. When the heat is absorbed, the temperature of the vapor will be very low, so it will now condense and change into water. And whenever water touches conductive parts of electronics and electrical component, there is every tendency it causes failure, because it can connect two terminals that are not supposed to be connected, or it can at least reduce the overall resistance, which will allow too much current to flow, and too much current flowing can bring about destruction in the system. So therefore, the humidity brings about reduction in the insulation resistance, and it also encourages the growth of a fungi. We know the fungi is microscopic organism, and it exists wherever there is water or dampness. So the existence of this humidity will bring about the growth of this fungi, and whenever this fungi is existing, it has potential, because it has density, moisture in it, it has potential of reducing the insulation resistance. Reduction in the resistance increases current. Increase in current increase the heat generation and can damage the system. And one thing we need to know is that supposing we have certain volume of water vapor in the air, so the level of humidity, that is the water vapor that condenses, will increase whenever the temperature falls, and that's what I explained. When the water enters the enclosure of an electronic system, for example, and the temperature in that air is absorbed, you see that the water vapor in that air will now condense, and that can cause the problem we have mentioned. So if humidity has problem in tampering with the durability and reliability of any electronic and electrical systems, how do we remedy it? The first thing is to use insulating materials to case our equipment so that there is no way this moisture can touch the components. And another way is to prevent moisture absorption and water film formation as a way of what? Preventing the growth of the fungi. What we are saying here is that if we provide a means that will reduce or eliminate the possibility of condensing water vapor inside our enclosures, then there is no moisture. If there is no moisture, definitely fungi will not grow, and if it didn't grow, all those effects we have mentioned, it will not cause. And the typical material we use for that is polystyrene. It's a good material for that insulating to prevent the entrance of this water vapor. Now we come to the mechanical vibration, that is the vibration due to mechanical energy. And we know whenever anything is subjected to vibration, it can suffer these problems. The support can become weaker, and the wires connections, they can become very loose because of vibration. This is a common knowledge. And if the vibration is very strong enough, it can bend and damage some components. So there is one important thing we should know. This vibration, in reality, it has very insignificant effects on electronics components which are very small, like resistors, like capacitors, like diodes. No matter how the amount of vibration, it hardly affects them because of their small size. Saying that it has insignificant effect, we are not saying that you should carelessly put your electronic component where they should be subjected to this. This is just an information. And also the electromechanical components, those components that consume electricity and maybe produce mechanical motion, like relays, like transformers, they are severely affected by mechanical vibration. So if they are affected, what is the way out? The remedies to this problem is using what we call anti-vibration mountings, and using shock-proof washers, and using locking nuts, and of course enclosing the sensitive component with some protective materials in such a way that they are prevented from shaking. These three items I have mentioned, my second lecture has given more explanation on them and the pictures of all of them. So I encourage all the students to try to watch the second part so that they will see pictures of this and their examples. At this point, we come to the end of the second segment of part 1 of this lecture, and the remaining items of the causes of failure, as we have seen, the environmental and the operating, they are all explained in the second part of the lecture. I thank everybody for taking his or her time to watch this, and I advise you to watch it over and over again. It will make your understanding stronger. Thank you very much.